Good morning, my dear students. Today's topic is carbonyl compounds, that is aldehyde and ketones. So first we studied the preparation of aldehyde and ketones, then chemical reactions of the aldehyde and ketones. So I start with the preparation of aldehyde and ketones. Preparation. First preparation is from oxidation of alcohol. Oxidation of alcohols. When 1 degree alcohols oxidized with the mild oxidizing agents like PCC, this is pyridinium chlorochromate, and alcohol is 1 degree. This is the mild or weak oxidizing agent. So aldehyde is produced. So 1 degree alcohols gives aldehyde. 2 degree alcohols gives ketone. So it is 2 degree alcohol. The product is ketone. So this is the first preparation of alcohol. Now come to the second preparation. Dry distillation of calcium salt of carboxylic acid. Second preparation is dry distillation of calcium salt of carboxylic acid. Means calcium salt of carboxylic acid heated at higher temperature, then carbonyl compounds are produced. So I write one simple reaction. Suppose I take a carboxylic acid, 2 molecules are taken. On reaction with calcium hydroxide, that is slaked lime, on reaction with, this is the acid base reaction, water is eliminated from this. The calcium salt is obtained. When this calcium salt is heated at higher temperature, then calcium carbonate is eliminated. That is, this is the portion which is eliminated by cyclic transition state, and finally we get the RCOR. So it is a trick to find the product. First identify the acid RCOOH, take 2 molecules, then final product contains RCOR, and the calcium carbonate is the byproduct for this reaction. So I write few examples. First example is like this. Suppose I take the formic acid. So on reaction with calcium hydroxide, salt of formic acid is obtained. On heating, after removal of calcium carbonate, the formaldehyde is the final product. So we can prepare the aldehydes. Suppose I take the acetic acid. So we get the salt of acetic acid, calcium acetate. On heating this, RCOCH3, that is CH3COCH3. So acetone is the final product. Suppose I take the mixture of 2 different acids, formic acid plus acetic acid on reaction with calcium hydroxide, then we get the 3 different salts. One is the salt of formic acid, that is calcium formate, another is the calcium acetate, and the third one is the mixed salt, So here we get the mixed salts. So on heating with this mixed salt, so total 3 products are obtained. The first is formaldehyde, second is acetone, and the third is acetaldehyde. So total 3 products are obtained by the mixed anhydride, mixed salt of the calcium carbonate. Next, suppose I take dicarboxylic acid, like this. 1, 2, 3, 4, 5, 6, 7. Suppose this is the heptanoic acid, heptane dioic acid. So on heating with calcium hydroxide, we get the salt of this acid, and heating calcium carbonate means one carbon is removed in this reaction, and finally 6 atoms are present in the final product. So cyclic ketones can also be prepared by this reaction. Suppose I take the adipic 1, 2, 3, 4 acid. So 1, 2, 3, 4, 5, 6. So on reaction with calcium hydroxide, we get the salt like this. On heating, five-member ring is produced because there are 6 carbon atoms and 1 carbon atom is removed in the calcium carbonate. So finally, compound obtained having 1 carbon less than the original number of carbon in the acids. Now come to the third preparation. Weaker process. In this, alkenes are taken in presence of PdCl2, oxygen, water. On heating, H and O are added to this, and alkene oxidized into aldehyde. So ethene oxidized into aldehyde, but other alkenes oxidized into ketones generally. Suppose R write RCH2CH2 plus PdCl2, the same reagent. Then the major product is ketone. So other alkenes generally gives ketones. So this is the third preparation. The next preparation for carbonyl compounds by reduction reactions. So first, reaction of acid halide with H2PD BaSO4. It is known as Rosenmund reduction. So RCOCl converted into aldehyde with Rosenmund reduction. So this is also a preparation of aldehyde. The second is reduction of ester or nitriles with diisobutyl aluminium hydride. So dibyl H or diisobutyl aluminium hydride is used to reduce ester or nitrile into aldehydes. So I take the example, suppose I take the ester like this, OET. Then by reaction with dibyl H at low temperature, minus 78 degrees centigrade. So RCHO is the product and ETOH is the byproduct. This is the main product and this is the byproduct. The second, if I take the cyanide, dibyl H after hydrolysis, again the final product is aldehyde. So this is the fourth preparation. Again, next reduction may be Stephan reduction. So in case of Stephan reduction, cyanide react with SnCl2 and dilute HCl. Then we get the aldehyde as a final product. So these are the reduction reactions: Rosenmund reduction, ester nitrile reduced with dibyl H, and Stephan reductions. Next preparation, oxidation of alkenes and alkynes. By ozonolysis reactions. So alkenes on ozonolysis in presence of zinc oxidized into aldehydes and ketones. B, that is hydration of alkynes. There are two different hydration reactions. Suppose I take the hydration in presence of mercury. Then Markovnikov addition takes place and ketone is the final product. This is by Markovnikov addition product. But if I take diborane, then H2O2 in basic medium, then aldehyde is the final product. This is according to anti-Markovnikov addition product. So these are the preparations of carbonyl compounds. There are many other preparations which we have studied in the previous chapters. For example, Fiedel-Crafts reaction was the one of the reaction, Fiedel-Crafts acylation. Another oxidation with the copper of alcohols. 1 degree alcohols give aldehyde, 2 degree alcohols gives ketones. And some other reactions, Itard reaction, Gattermann-Koch reactions are used to prepare carbonyl compounds in different reactions. Now I come to the chemical reactions of carbonyl compounds. Now write the chemical reactions of carbonyl compounds. Characteristic reaction, that is very important. Characteristic reaction of carbonyls is nucleophilic addition reaction. This is very important, nucleophilic addition reaction. Reason behind this is because structure of carbonyl is like this, C double bond O. So it is partial positive and negative are present on the carbonyl group, and carbonyl carbon act as electrophile. Carbonyl carbon acts as electrophile. So nucleophile add to that carbon and give nucleophilic addition easily. So characteristic reaction of carbonyl compounds are nucleophilic addition reaction. If we know the main reaction, that is characteristic reaction, then we can easily find the products and check the answers. So I write the general reaction. General reaction is like this. Suppose I take this carbonyl compound. Suppose a reagent contain electrophile and nucleophile. Then nucleophile add to the carbon, electrophile add to the oxygen atom. Electrophile is generally water. Electrophile is generally H plus. Generally. So this is the general reaction. Pi bond is broken, nucleophile add to the carbon and electrophile add to the oxygen atom. So come to the mechanism part. Mechanism. There are two different mechanisms. One is in acidic medium, another is in basic medium. So I take first in basic medium. In basic medium, nucleophile directly add to the carbon and pi bond is broken. This is the nucleophile. Now in second step, hydrolysis takes place. So H plus or H2O, then O minus gain the proton, and finally product is like this. Nucleophile add to the carbon, electrophile add to the oxygen. This is the final product. In this mechanism, first step is slow, that is RDS step. Second step is fast. Nucleophilic addition is also possible in acidic medium. So mechanism in acidic medium. So in acidic medium, first H plus reacts. So by the polarization, oxygen gain the proton and intermediate carbocation is formed. This reaction is fast and reversible. In second step, the nucleophile react to the carbonyl carbon, that is on the positively charged. This step is slow, so generally RDS. Again product is same. The same products are obtained. Nucleophile attached to the carbon and electrophile attached to the oxygen atom. So this is the mechanism. In both the mechanism, one thing is common. In the basic medium, first step is RDS, that is attack of nucleophile. In acidic medium, second step is RDS, that is again a take of nucleophile. So in both the case, a take of nucleophile is the RDS step. Now come to the reactivity orders. Rate and reactivity of carbonyl carbon. Rate is directly proportional to, or you can write rate of nucleophilic addition. Is directly proportional to the partial positive of the carbonyl carbon. This is the very important first step. Partial positive at C double bond O. Second, you can write electron withdrawing groups, that is minus I minus M, also increases the rate. The next important factor is crowding. Crowding at C double bond O increases, so rate of nucleophilic attack decreases. So nucleophile attack with the slow rate because of crowding effect. So it is very important. So rate is inversely proportional to the crowding of C double bond O. Again, resonance effect in C double bond O. If resonance effect is present in the C double bond O, then the partial positive charge decreases because of resonance effect. Charge is delocalized and distributed between the different number of carbon atoms. That's why rate decreases. Or you can say electron releasing effect. So plus I plus M also decreases the rate of reaction. So this is a very important part of the carbonyl compounds. So I write some questions. Question number 1. Compare the rate and reactivity of the following compounds. So first, suppose I write the formaldehyde, then other aldehydes. Now come to the ketones. Acetone is the smallest ketone in open chain structure. Now acetophenone. Now next is suppose benzophenone. So compare the rate of these compounds. This is a formaldehyde and acetaldehyde. So one methyl group added to the carbonyl carbon. So it creates crowding. So rate decreases. Again CH3 replaced with the phenyl group. So phenyl group give resonance effect with C double bond O. That's why positive part decreases. So positive charge decreases, rate decreases. Again crowding increase because there are two alkyl groups. So crowding increases, so rate decreases. Again resonance effect increases, so rate also decreases. So in general we can say aldehydes are more reactive than ketones. These are normal aldehydes and these are the normal ketones. So generally we can say in carbonyl compounds aldehydes are more reactive than ketones. Suppose I take the second question, in case of cyclic compounds. Here is a 3-membered ring, then 4-membered ring, then 5-membered ring, then 6-membered ring. So this is a strained ring. highly strained. So that's why this is more reactive as compared to the other things. So strain is high, there is minimum strain. So because of strain, reactivity increases. Suppose I take the next example, benzaldehydes. Suppose I write here NO2, CH3, OCH3. So CHO is common between all the four examples, but NO2 group increases the partial positive. That's why reactivity of the nitro compounds is more as compared to the simple benzaldehyde. And methylated benzaldehyde is less reactive because of plus I plus H group, and plus M groups again further decreases the rate of reaction. So you can say minus I minus M increases the positive charge, plus I plus M decreases the positive charge. This is the basic difference. In general, aldehydes are more reactive than ketones towards nucleophilic addition reaction. Aldehydes are more reactive than ketones. Now come to the individual reactions, addition of different nucleophiles. So till now we have studied that carbonyl compounds gives nucleophilic addition reactions in both medium, either in basic or in acidic medium. Now first addition. Addition of HCN, hydrogen cyanide. So in hydrogen cyanide, it is converted into H plus and Cn minus. So Cn minus was the nucleophile. Reagents are, that is important. We can take directly KCN and H plus, or we can take NaCN, H plus or H2SO4. Here also we can write H2SO4. Third, if I take the HCN directly, then use dilute base. So dilute base is used because HCN is weakly ionizable acid. It is used to ionize HCN easily because it is weakly ionized acid. So it directly does not give Cn minus. So these are the reagents. We can take any one of them. Questions are like this. Suppose I take CH3, CHO, KCN, H plus is taken. So Cn minus add to the carbon, H plus add to the oxygen. So final product is cyanohydrin. It is known as cyanohydrin. Suppose second example, SCN or dilute NaOH. So in this case, it is a cyclic ketone So Cn minus add to the carbon and H plus to the oxygen atom. So this is Cn and OH. Again, this is a cyclic cyanohydrin. So cyanohydrin is the major product in case of addition of HCN, hydrogen cyanide. Second addition, addition of lithium aluminum hydride or sodium borohydride. The same nucleophile is H minus. So reaction is like this. So I take the example. So this is the carbonyl compound. First I take lithium aluminium hydride in presence of ether. So H minus go to the carbon and intermediate is formed. In second step, after adding the water or hydrolysis, it take H plus from the water. So this is the final product. Final product is alcohol. Nucleophile at the carbon and H plus at the oxygen. Suppose in the same reaction, I take lithium aluminium deuteride. So this is the final product. Suppose in the same reaction I take NaBH4, then H minus is the nucleophile and D2O. So OD is the final product. So this is the addition of lithium aluminum hydride or sodium borohydride. It is also known as reduction reaction because both nucleophile and electrophiles are H atoms. One is H minus and another is H plus. Third reaction, addition of Grignard reagent. Grignard reagent is RMgX. RMgX acts as strong nucleophile or a strong base because it is an organometallic compound and it acts like this, R minus Mg plus. So R minus act as nucleophile in this reaction. So products may be 1 degree, 2 degree, 3 degree alcohols depending upon the nature of carbonyl compound. So in first example, suppose I take formaldehyde with RMgBr in presence of ether because Grignard is always prepared in presence of ether. So R minus I take to the carbonyl. So RCH2O minus MgBr is the salt. After hydrolysis, in the second step, O minus take the water molecule and 1 degree alcohol is obtained. Suppose I take the another aldehyde, any other aldehyde, suppose CS3CHO. So by the same reaction, so 2 degree alcohols are obtained. So it is 2 degree alcohol. So formaldehyde gives 1 degree alcohol, but other aldehydes gives 2-degree alcohols, and ketone gives 3-degree alcohols by addition of Grignard agent, because Grignard agent have a one alkyl group also. So in the next example, I take the ketone. Suppose I take acetone by taking the same Grignard agent, CS3R, CS3O minus. This R is obtained from Grignard agent. So after hydrolysis, 3-degree alcohol is obtained. So we can produce 1, 2, 3-degree alcohols by reaction of carbonyl compounds with Grignard agents. So next question is for you. Suppose a carbonyl compound is taken. B is the Grignard agent. After hydrolysis, C2H5 CH2OH is obtained. So find the A and B. So trick is like that. Carbon having OH group is also having a groups obtained by Grignard. So this is the Grignard portion and this is the carbonyl portion. So you can write the answer like this. A is formaldehyde and B is C2H5MgBr. The next question, suppose I take a carbonyl compound A, Grignard agent B, on hydrolysis, we get a compound like this, PHCS3 ethyl OH. This is a 3-degree alcohol. So this carbon contains alcohol. So you can see here 3 different groups are present or attached with this carbon. So 3 possibilities of Grignard agent. You can take methyl, you can take phenyl, or you can take ethyl as a Grignard. So rest part are the aldehyde and ketones, carbonyl compounds. So solution of this is, if A is this portion, phenyl CH3O. Suppose A is phenyl CH3O. So in this case, B is ET-MgX. This is the first combination. When ethyl add to this carbon, the same product is obtained. So it is the first combination. If A is PHCOET, then B should be CS3MgX. This is also a correct combination. If A is CS3COET, then B is PHMgX. So there are 3 different combinations we can use to produce the same alcohol. This is very important reaction, addition of Grignard. Now come to the next reaction, 4th reaction. Addition of sodium bisulfite. Generally, aldehydes react with sodium bisulfite. As the crowding increases, rate of addition decreases, and in this case, addition does not take place very easily. So as the crowding increases in ketones, addition becomes difficult of sodium bisulfite. Addition of sodium bisulfite becomes difficult. Product is sodium bisulfite salt. In a crystalline form. CS bond is obtained in the product. So reaction is like this. Suppose I take any aldehyde RCHO plus sodium bisulfite. Then this sulfur take to the carbonyl carbon, because sulfur is good nucleophile as compared to the oxygen. This intermediate is formed. After H plus exchange, we get the final crystal. So this is the addition of SO3 at carbon atom and hydrogen at oxygen atom. So this is in crystalline form. So crystals are obtained. This reaction is used to isolate the aldehydes or purify the aldehydes from the mixtures, because this crystal is easily hydrolyzed and again converted into the same aldehyde in the pure form. Hydrolysis of bisulfite crystals. In acidic medium. This is unstable. So after removal of water, pure aldehyde is obtained. So that's why its application is this reaction is used to separate and purify the aldehyde from mixture. So sodium bisulfite addition, I repeat the same. Generally I use for aldehydes, not for ketones, because ketones are very less reactive or sometimes reaction becomes very difficult. Product is sodium bisulfite salt. It is in crystalline form. CS bond is obtained. Carbon sulfur bond is obtained. Sulfur acts as a nucleophile. Mechanism is nucleophilic addition. So nucleophile add to the carbon and hydrogen add to the oxygen atom. And this crystal is easily hydrolyzed in acidic medium, and after hydrolysis it gives pure aldehyde. That's why this reaction is used to separate and purify the aldehydes from the mixture. The next addition reaction is addition of water. It is a reversible reaction. Generally, K minus 1 is greater than K1. That is rate of backward reaction then rate of forward reaction. Product is ZM diol. This product is unstable. Therefore, reaction is reversible and rate of reversible reaction is greater than forward reaction in many cases. But in few cases, first I write the reaction. Addition of water, that is hydration. So RCH, OH and OH. This is same diol. This is K1 and backward is K minus 1. So generally K minus 1 is faster than K1. Now some carbonyl compounds give stable ZM diol. And then K1 is greater than K minus 1. For example, first CCl3CHO. It is known as chloral. This molecule is stable because of hydrogen bonding. For example, I write the structure in this way. This is the hydrogen bonding case, butterfly-like structure, and it is stabilized by the intramolecular hydrogen bonding. So it is highly stable and rate of forward reaction is greater than the rate of backward reaction. The similar example is fluoral, CF3CHO. This is fluoral. So again, it is stabilized by hydrogen bonding. So it is again a stable product. So rate of K1 is more than K minus 1. Third example is formaldehyde. So in case of formaldehyde, it is also more stable because of hydration, highly reactive also. Next is cyclopropanone. So it is the less strained. So because of strain release, so strain release, that's why reaction goes forward. So it is the strained. This is less strained. And one more example in which rate of forward reaction is greater than the rate of backward reaction. This is ninhydrin. This molecule is known as ninhydrin. So water add to the central carbonyl carbon. Stable due to intramolecular H. So in all the above cases, rate of forward reaction is greater than backward reaction. Or you can say rate of hydration is much greater than the rate of hydration with other aldehyde and ketones. So I write this: rate of hydration is more for the above 5 examples than the other carbonyl compounds. So in general, addition of water is difficult because of reversible reaction, but in few cases like chloral, fluoral, formaldehyde, strained ring, or such type of rings in which 3 carbonyl groups are present on adjacent atoms and they can form hydrogen bond in products. Now the next addition is very important addition of alcohol. Reagents are alcohols plus dry HCl or H plus or HCl gas. Alcohol means simple alcohols. We can take glycols or polyols. We can also take thiols, and H plus. So addition of alcohol is possible in acidic medium only. Acid should be pure or dry HCl gas is used. Water should not be present in this case. If water is present, then reaction becomes reversible and again reactant is produced. So I write the general reaction. So you should learn the general reaction first. Suppose I write one aldehyde with 2 moles of ETOH in presence of H plus or HCl gas. So this reaction is produce acetal. 2 ethers present on the same carbon atom. So 2 moles of alcohols are added in this reaction, but this reaction becomes reversible if dilute HCl or H3O plus is taken. So again hydrolysis takes place and pure aldehyde is again obtained. So it is very essential to take care about the acid. If dilute acid is taken, then reaction becomes reversible. Addition is possible only in presence of strong acid or HCl gas or pure H plus. Now come to the mechanism part. Suppose I take the same example in the mechanism. RCHO in first step, in presence of acid, oxygen take the proton. This step is reversible. Carbocation intermediate is formed. The first alcohol molecule is added to the carbonyl group, that is OET. H is removed from this reaction. Again, suppose H plus is given, so OH is converted into good leaving group, that is OH2 plus. It releases the water molecule, RCH, OET, and carbocation is formed again. Again taken the second molecule of alcohol, removal of H plus. So acetal is obtained. If I take the ketone, then ketal is the final product. So this intermediate is known as hemiacetal, in which one ether and one alcohol group is present. And when two ether groups are present, then it is known as acetal or ketal. So I repeat the mechanism. Addition of alcohols takes place in presence of dilute dry HCl or H plus or HCl gas. You can take any type of alcohols, glycol, polyols, thiols, etc. General reaction is two molecules of alcohols are added in presence of H plus. Final product are acetal, or if ketone is taken, then known as ketals. Mechanism. In first step, H plus add to the oxygen, carbocation is formed, ETOH attack to the carbocation, because ETOH is a weak nucleophile, so it wait till the carbocation is formed. First intermediate is formed, hemiacetal, it gain the proton, OH group converted into good leaving group, and after removal of this water, again the second carbocation is formed, that is resonance is stabilized also. ETOH or the second molecule of alcohol attack on this, and the acetal or ketal is formed. So in this step, we gain the acetal, but in case of ketone, the ketals are major products. Some important points regarding this reaction. First point. Ketals or acetals are the final products. Intermediates are carbocations and hemiacetals. Third, this reaction can use to protect the carbonyl group from nucleophile or base. Reason behind it, acetal and ketals do not react with nucleophile or base. This is the basic theme. So I write few questions. Suppose question number 1. This cyclic ketone is taken and MeOH is there, okay, in presence of H plus. So 2 moles of MeOH are used. So this product is obtained. The question number 2, suppose I taken the same type of carbonyl group on reaction with glycol and HCl, then the one molecule of glycol is sufficient for the complete reaction, because two OH group react simultaneously one by one. In the first case, hemiacetal is formed. After removal of water, then again the same OH react with the carbocation. So this is the product. This is cyclic ketone. The next example. Question number 3. Suppose I take the thiol, ETSH plus. So again, two molecules of thiols are added, and this is thioketal. So obtained. We can use the thioglycol also. So PHCH SCH2 SCH2. So cyclic acetal is also, cyclic thioacetal is formed. Now the application part is, suppose the fifth example. We should convert ester into alcohol, but aldehyde remains as it is. So this is the target. Aldehydes remains as it is and ester is converted into alcohols. So it is directly not possible without the reaction with aldehyde, because all the reducing agent react with aldehydes faster than ester. So if I take the lithium aluminum hydride, aldehyde reacts fast, but ester does not. That's why this product is not possible directly. So solution is like this. In the first step, I used to protect the aldehyde group by any one of them alcohol. Suppose I take ETOH and H plus. So in this case, OET is formed. Now this is the ether group and it does not react with the lithium aluminum hydride or any base. Now ester can react with lithium aluminum hydride. So in the second step, only ester reacts, but ethers does not. Now in the third and last step, I use the acidic hydrolysis. In acidic hydrolysis, acetal and ketals breaks down into aldehyde and ketones. So there are 3 steps to convert this compound. So this is the addition of alcohol. I repeat the complete topic which we have studied today. So initially I started with the chapter carbonyl compounds, aldehyde and ketones. First I take preparations by different methods: oxidation of alcohols, digestion of calcium salt, of carboxalic acid, some reductions of esters and cyanides, and some oxidation of alkenes and alkynes, and many more reactions are there to prepare the aldehyde and ketones. Now the chemical reaction of aldehyde and ketones. So very important chemical reaction is nucleophilic addition reaction. So in nucleophilic addition reactions, it is possible in acidic medium as well as in basic medium. So in both medium it is possible. So I started with the mechanism. So on the carbonyl compound, C attached with the nucleophile and oxygen attached with the generally H plus. So general product is nucleophile at the carbon and hydrogen at the oxygen atom. First, reactivity part. So reactivity of carbonyl compounds depends upon the partial positive charge at the carbonyl carbon. If the partial positive charge increases, rate of reaction increases. Generally, aldehydes are more reactive and ketones less because of crowding effect, because of electronic effects. Due to the both reasons, ketones are less reactive. Now examples. First, addition of cyanide, addition of SCN. So product is cyanohydrin. CN add to the carbon and hydrogen add to the oxygen atom. Second addition of Grignard reagent. So product is alcohol 1 degree, 2 degree and 3 degree. Now third addition, sodium bisulfite. So generally aldehydes react with the sodium bisulfite but ketones does not. And it is used to separate the aldehydes from the mixture. Next, addition of lithium aluminum hydride or sodium borohydride, that is also known as reduction reaction. The next part is addition of water, that is hydration. Hydration is a reversible reaction, but in few examples this reaction is possible and goes towards the forward direction because product is stable due to the hydrogen bond or some other reasons. The next reaction is addition of alcohols. So it is very important. So it is used to protect the carbonyl group from the basic reagent also. So now last I write two examples more. Stereochemistry of the addition reaction. Stereochemistry of the addition reaction. In the first example, suppose compound is achiral compound, and if I add cyanide in presence of H plus, then cyanohydrin is obtained and a new chiral center is obtained. This compound is chiral. So there are two products are obtained. In the first product, suppose OH group on the right side, then in the second OH group at the left side. Both are the enantiomer of each other. So product is a racemic mixture, D plus L mixture, pair of enantiomers. So in this case, total products are 2. Similarly, one more example. If one chiral center is already present, suppose one chiral center is already present, then addition takes place. So a new chiral center is obtained. But the previous chiral center unaffected. This is a new chiral center. This is the previous chiral. It is unaffected in this reaction. So total again 2 products are obtained because of only one new chiral center. So these are the 2 products, and products are pair of diastereomers. Suppose I take the example like this. Then the reaction takes place at carbonyl carbon. Again, Two products are obtained and both are geometrical isomers. Total products 2 and relation is geometrical isomers. So this is the end of today's lecture. Thank you.